Hello, everybody. Welcome to Module 4, Lesson 4. This is going to be the culmination of everything that we've done in the previous lessons. So we're going to take our Lewis dot structures, we're going to take our polarity, our intermolecular forces, we're going to put it all together, and we're going to talk about VSEPR and how all of these things relate. So VSEPR stands for valence shell electron pair repulsion theory, and it states that the repulsion between electron pairs causes molecular shapes to adjust so that the valence electron pairs stay as far apart as possible. So basically, the bonds want to be as far apart as possible, and in order to do that, or what does that, is the lone pairs. And we're going to see examples of that. So the bond angle is just the angle between the bonds, which is something that you're going to have to know. So our first shape that we're going to look at is a linear molecule, and this is it down here to the right. A linear molecule, it has 180 degrees between bonds. It has one central atom with two atoms bonded to it, and there are no lone pairs around the central atom. So that's one way you could have a linear molecule, and this isn't the example we're going to look at. We're going to look at carbon dioxide. So CO2, as we know, looks like this, with our little lone pairs on the oxygens. Okay, so you can see that there's one thing in the middle, one central atom. It's bonded to two other atoms, and there are no lone pairs around the central atom. Okay, so this angle here, when it says bond angle, between the bonds is 180 degrees. That's as far apart as those bonds could possibly be from each other, and that's great because we know that electrons repel each other, which is the whole electron pair repulsion theory. And so then you get your linear shape. You could also have a linear molecule that has one central atom, two bonded atoms, and three lone pairs. I'm going to show you what that looks like in a second. So I'm going to show you a website, and this link will be posted in the online lab that you're supposed to do. But here's our central atom. If we look at carbon dioxide, it has two double bonds, so I'm going to add two double bonds, no lone pairs around it. You can see the bond angle is 180, and if you look down here, the molecular geometry is going to be linear. So let's remove everything, and let's add two bonds. It doesn't matter if they're single or double, so two bonds, which we know is that. And now let's add three lone pairs. Look at that, it goes back to being linear. Okay, so the three lone pairs, they orient themselves so that they can be a linear molecule, and those bonds and atoms or electrons are as far apart from each other as possible. Now, let's talk about polarity. Let's look back at our example for CO2. Okay, the polarity between carbon and oxygen is one that I said that you're definitely going to have to know, and we know that the CO bond is polar. Okay, so what happens is that the electrons get pulled towards the oxygen because that's the more electronegative element. And then if we remember from our last one, we put the line at the end where the thing is positive. So the electrons are going towards the oxygens. This makes that partially negative. It makes the carbon partially positive. But what ends up happening, it's like a tug of war. If I get pulled in that direction and in that direction with the same force, these pulls cancel each other out. And therefore, the molecule is nonpolar. So if the poles can cancel each other out, they're in equal, or they're in opposite directions with the equal force, they're going to cancel each other out and make the molecule nonpolar. Okay, so since this molecule, and remember we talked only about bond polarity last time, but if we're in this one, we're talking about the whole molecule, which is the important part. You want to pay attention to that. If it doesn't specify, it's talking about the molecule, not the bond polarity. So since this molecule is nonpolar, that means the only intermolecular force that it has is London dispersion forces. Okay. So that's it for linear. And what I highly suggest is with this information on one side of a flashcard, do linear and then write the parameters. So you would have both of these well, the other one ran away, not ran away, it got deleted. Okay, so let's go to the next shape. I'm going to do a couple more slower, but then I'm going to kind of go through these pretty fast because there are a few of them that we're going to look at. The next one's trigonal planar molecule. It's 120 and it's flat. So let me show you what that looks like in this simulation. So one central atom with 3 atoms bonded to it, 120 degrees. That's a flat trigonal planar molecule. So again, one central atom, 3 bonded atoms, no lone pairs. And if we just look at the shape of that molecule, if you look at the trigonal planar, you could probably tell that this thing will be able to cancel out its polarity. If you get pulled in, let's see if you can do this. If you get pulled this way, that will overall be a downward pull. Because if I go this way and this way, overall, it's like you're pulling down. And then you have something pulling up that can cancel. And so therefore, this thing will be able to cancel out its polarity. So trigonal planar molecules can cancel polarity. Okay. Our example here is boron trifluoride. Remember, boron is one of those things that's totally okay, breaking the octet rule with just 6. All right, so the fluorine we know is the most electronegative element. So if you get pulled in that direction, and that direction, overall, these will cancel out your polarity. Therefore, this will be nonpolar molecule. MOL apostrophe C is the abbreviation for molecule. And it will have London dispersion forces as its intermolecular force. Okay. So our next shape is tetrahedral. It's 109.5 degrees between these angles. There's one central atom with 4 bonded atoms and no lone pairs. So if we look at this, here's my trigonal planar. If I add a 4th bond, here is my tetrahedral. Okay, so you can see what it looks like. You can move it around. So what's going to happen is there's going to be a pull in slightly downward for all of those. So let me orient this in the way that will make sense. Okay, so these are, you can see, they're going out and down, and this one's going back. So overall, these 3 pulls will be down, and then we have our pull up that will end up canceling. So tetrahedral molecules, they can cancel. So our first example is CH4. And if you remember anything from our polarity lesson, CH4, the CH bond is nonpolar. If you have all nonpolar molecules or nonpolar bonds, the molecule has to be nonpolar. So CH4 is nonpolar, and it has London dispersion forces only. Now remember, hydrocarbons are always nonpolar, and they only have London dispersion forces. Let's try something, and let's change one of those H's to a fluorine. So now there's a pull going up, and all of those have no pull. So this will end up being polar. And if we have a polar molecule, this thing is not having fun. It's going to be dipole-dipole interactions and London dispersion forces. Okay, so just by changing one of those atoms from hydrogen to fluorine is more electronegative than the carbon. It pulls the electrons towards it, makes the molecule polar, and then you have dipole-dipole interactions. Now, I'm going to change all of the H's to fluorines, and let's see how that will affect it. So CF4. Of course, your lone pairs. So the carbon fluorine is the most electronegative. This is going to be a polar bond. So, and we know this isn't what it looks like in reality. It looks like this, but this is the way our Lewis dot structure shapes it. Now, that's one of the important things to note when you're doing this. Just because your Lewis structure looks like something doesn't mean that's what it actually is. That's why you have to understand what these parameters are for each of the molecules shapes, because what you draw is not necessarily what it's going to look like. So now, since I have all the same bonds, carbon, fluorine, and they're all equal poles, they're all in opposite directions. So CF4 ends up becoming nonpolar because of the shape. Because tetrahedral molecules can cancel out, since they're all the same bond, it's going to be a nonpolar molecule. Okay. Two more of our basic shapes, and then we're going to go into shapes that can break the octet rule. So trigonal pyramidal, here's our first one that has a lone pair. It's 107 degrees between the bonds, one central atom, 3 bonded atoms with 1 lone pair. And our example is NH3, which is ammonia. Okay. So nitrogen, bond your 3 hydrogen, and then nitrogen has a lone pair here. So we can look here, the nitrogen-hydrogen bond. Okay, that's going to be a polar bond. Overall, ammonia is a polar molecule. And it's going to have dipole-dipole for sure, because it's a polar bond. Remember, everything has London dispersion forces. And then what about hydrogen bonding? Remember, hydrogen bonding when a partially positive hydrogen bonds to a fluorine, oxygen, or nitrogen. Well, the nitrogen is partially negative. That's the more electronegative. It makes these hydrogens partially positive. So if I had another ammonia molecule, I could have a partially negative nitrogen be attracted to a partially positive hydrogen of another molecule, and so it will also have hydrogen bonds. So ammonia will have all 3. Please note, and then here, I'll show you in here. So for the trigonal pyramidal, we lose a bond and it gets replaced with a lone pair, and you can see you have a trigonal pyramidal molecule. Trigonal pyramidal molecules, they have nothing to pull it back up. This lone pair doesn't pull the electrons towards it. So trigonal pyramidal molecules cannot cancel. Okay. Bet molecules, 2 lone pairs, 1 central atom, 2 bonded atoms like H2O. You know that one. we know it's not going to be able to cancel, because we all know water is polar. This is a polar molecule, and it has all three IMFs, intermolecular forces. You may also, for bent, it could be one central, two bonded, with one lone pair. Okay, so the only thing that would change would be the bond angle, but it would still be considered a bent molecule. Okay, so now we're getting into the molecules that break the octet rule. All of these are going to have more than 8 around their central atom. And I'm going to go through these a little quicker. So first one, Trigonal Bipyramidal. It looks like a linear molecule and a trigonal planar molecule that have been put together. Depending on which bond you're talking about, you can have a 90, a 120, or a 180 bond. It's one central with 5 bonded and no lone pairs around the central atom. And our example is going to be PCl5. So phosphorus pentachloride, 1, 2, 3, 4, 5 chlorines, of course, with their lone pairs. Trigonal bipyramidals, they can cancel. But remember, in order to be able to cancel polarity, they have to have equal and opposite poles. So these are all opposite poles. They're all equal since they're all the same bond. And this will be a nonpolar molecule. If it's nonpolar, it only has London dispersion forces. The next one, octahedral, one central with 6 things bonded to it and no lone pairs. You can see it's basically 3 linear molecules put together, which means octahedral can cancel. Okay, so our example is sulfur hexafluoride, sulfur in the center, 1, 2, 3, 4, 5, 6 fluorines. Of course, with their lone pairs. So it can cancel. They're all the same bonds. This is a nonpolar molecule. And it is going to have, again, just London dispersion forces because it's nonpolar. Okay, the next two, Seesaw. I mean, if you had a little person here and here, it looks like a seesaw. So sometimes scientists aren't that creative. They're just literally naming it what it looks like. Bond angles, 90, 120, 180, again, depending on between which bonds you're talking about. One central atom with 4 bonded atoms and 1 lone pair. On seesaw molecules, that lone pair means it cannot cancel its polarity. Sulfur tetrafluoride, lone pair up here. It looks like a linear with a bent, and we know bent molecules can't cancel. So this is going to be polar. Any bond with fluorine is going to be polar. So keep that in mind because it is the most electronegative element, except for with fluorine. So when fluorine bonds with itself, it's nonpolar, but when fluorine bonds with any other element, it's going to be polar. So this molecule is polar. It's going to have dipole-dipole for sure because it's a polar molecule. And it's also going to have London dispersion forces because everything has London dispersion forces. This thing will not have fun because there's no hydrogen in it. Okay. Then we have a square planar molecule. It's flat, so it's just 2 linear ones. And you can basically tell it like that. And it's going to, it can cancel. Even though it has 2 lone pairs, it is able to cancel because it is a planar, a flat molecule. One central with 4 things bonded to it and 2 lone pairs, basically 1 on the top and 1 on the bottom in that example. And so we have xenon tetrafluoride, 1, 2, 3, 4, fluorine, 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 fluorine. Now I'm going through these Lewis structures fast because at this point you should be fairly good at this. Plus we have seen this one before. So this one has all the same bonds, even though the bonds are polar. This is a nonpolar molecule. And it will only have London dispersion forces. Okay. Last two, we have square pyramidal. So it was a square planar, but it's got a bond on top. It takes one of those lone pairs and puts a bond on top. And then it's got one central, 5 bonded, 1 lone pair, 90 degrees between the bonds. This one cannot cancel. That lone pair here, nothing to pull it back down, so it cannot cancel. So IF5, iodine, pentafluoride, 1, 2, 3, 4, 5, with a lone pair. So again, this thing, the way I've drawn it, does not look like this molecule the way it has in this picture. So that's why, again, we must know our parameters. 1 central, 5 bonded with 1 lone pair. This is going to be a polar molecule because it cannot cancel out its polarity. Therefore, it will have dipole-dipole interactions and London dispersion forces. Again, it doesn't have hydrogen bonding because there are no hydrogens in it. And then the last shape for today, or not just for today, the last shape period, is my favorite. It's T-shaped, and it's my favorite because it's shaped like a T. You could not get more literal than that. So we've got 90 degrees between the bonds, 1 central with 3 bonded and 2 lone pairs. Boom, boom. And this one cannot cancel either. There's nothing pulling it back up. So chlorine trifluoride. There's my 2 lone pairs here. Okay. This one will be polar. Like I said, anything bonded with fluorine is going to be a polar bond, and it will have dipole-dipole and London dispersion forces. Okay. So that's it for the shapes. Please make sure you ask any questions. There are a couple more things that we're going to talk about, but that's it for the shapes. The next thing is just going to be a vocabulary term. A covalent network solid is basically covalent bonds that have a lattice structure. So we know lattice structures are for ionic compounds. You looked at that in the first lesson in this module. Covalent network solids, carbon, silicon, boron, they're the ones that like to do this, form these huge lattice structures. So it's a huge 3D lattice structure made up of strong covalent bonds. They have high melting points and are insoluble in water. So this one's diamond, graphite, and a buckyball. Buckyball is 60 carbons that are bonded together to give you that structure. So those are all carbon bonded in different lattice structures. That's known as an allotrope. So compounds that have the same element but is bonded in different formations. So diamond, graphite, buckyball, nothing but carbon, just bonded differently. That's an allotrope. And then another example is silicon dioxide. It forms a lattice structure. So these are the 3 elements that like to form network solids, covalent network solids. And then finally, we're just going to talk about hybridization. So a hybrid is basically you take 2 things, you put them together, and you get a new thing. So when we use the Vesper model, we create models of molecular shapes, but we need to look at the orbitals of the electrons. So basically, I'm going to summarize this for you. Hybridization is making the same bonds out of different orbitals. So for example, when we have carbon, it has a p orbital in its outermost. Hydrogen is just the s. So when these guys come to bond, remember it's overlap is the bonding. they end up having a bond, a molecular orbital that is hybridized and overall the same. So it's the same all over. It doesn't look like this. It ends up forming a hybrid to be in between the P and the S that's come together. So what we need to do is you only have to do one thing with these hybrid orbitals, hybridization, and let me show you what that is. So when you create hybrid orbitals, basically we're looking at sites for electrons. That could be either a bond or a lone pair. And depending on how many sites, that will be what your hybridization is. So if you have 2 sites, it's going to be sp hybridized, 3 sites sp2, 4 sites sp3. If you're breaking the octet rule, it will have 5 or 6 sites. 5 sites is sp3d, 6 sites sp3d2. Now, the thing after that, so to the left of this is the hybridization. To the right is the electron geometry. Okay, so the left is the hybridization, to the right is the electron geometry. Let's hold off on the electron geometry and let's look at the hybridization for ammonia. We already saw this, NH3 with a lone pair here. Now, when you do hybridization, it's typically for the central atom, or it will specify which atom it wants. So if we look at this, remember, any type of bond, so one site equals any bond, which is either a single, double, or triple, or any site is a lone pair. So if we look at the sites, the lone pair is 1 site, 2, 3, 4. There are 4 sites or areas of electrons around the nitrogen, which therefore makes it sp3 hybridized. So that's its hybridization. So if it's sp3 hybridized, its electron geometry is going to be tetrahedral. What is the electron geometry? It's basically looking at the electron cloud and saying, what is this shape? Okay, so if I go and show you here on this thing, if I do 1, 2, 3 and a lone pair, we know this is going to be ammonia. It's a trigonal pyramidal. Right here, I've got electron geometry. The electron geometry is what does the electron cloud's shape look like? So if you're just looking at where electrons were around here, then it would have a shape that is tetrahedral. So it's basically taking into account the lone pair, basically a bond in this situation. Okay. That's all we have to do with this. Count up the sites around it. If it asks for the electron geometry, it's related. Okay. Something that I've thought that's helped in the past, if you look 2 sites sp, count up the exponents and that will tell you the sites. sp, 1 and 1 is 2 sites. sp2, 2 and 1 is 3 sites. sp3, 3 and 1 is 4 sites. So that's just something that can help you. And then finally, skip this, not important. There's a bunch of examples. There's 6 examples. I'm going to stop the video here and ask you to do these examples, and the answers, I've done them. They are in the completed notes, okay? So that's it for this. I know this was long. Please make sure you ask your questions because this is basically everything that we've done in this module all wrapped in as one. All right, see you later.